Hi guys, this video starts section 9.6, which will teach us how to write Lewis structures for more complicated compounds. So there are some rules on page 386 of your book, and I've sort of summarized them here. I'm just going to read them quickly and then we'll do some problems. Number 1, draw the skeletal structure of the compound showing what atoms are bonded to each other. And sometimes when you have more than one atom, the question might arise, which one goes in the center? Well, the answer is you put the least electronegative element in the center. Number 2, you would count the total number of valence electrons that everybody has who is participating in that compound. So for example, if you have water, which is H2O, you would have to take the 6 valence electrons of oxygen and the 1 valence electron from both of the hydrogens. So in total, you would have to account for 8 valence electrons. Second part of that rule is add 1 for each negative charge and subtract 1 for each positive charge. That just basically takes care of all your ions, your cations and your anions. So of course, if you have something like a nitrate, that's NO3 minus, you would have to add up everybody's valence electron of the nitrogens and the 3 oxygens, but you would have to add another negative charge because it's NO3 minus. So you would have to account for a total of 24 electrons. Rule number 3. Complete an octet for all the atoms except hydrogen, of course, because hydrogen can only hold 2, so it's full at 2. And then number 4, if the structure contains too many electrons, after you complete everybody's octet, then you can start making the double and the triple bonds on the central atom as needed. So those are very general rules, so let's go ahead and do some problems. This is problem 9.3 in your chapter, and it basically wants us to draw the Lewis structure for nitrogen trifluoride, NF3. First thing you do is you have to count how many valence electrons are involved in this compound. So nitrogen has 5 and fluorine has 7, but you have 3 fluorines. So 7 times 3 is 21. 21 plus the 5 of nitrogen makes a total of 26 valence electrons. Next thing you do is you draw which one goes in the center. Well, nitrogen is less electronegative than fluorine, so nitrogen would obviously go in the center. Next thing you do is draw a bond between the nitrogen and each of those fluorines. That accounts for 6 electrons. So 26 minus 6 leaves you 20 valence electrons. The next thing you would do is complete their octets. So you would have 2, 4, 6, 2, 4, 6, and 2, 4, 6 for each of the fluorines. So the fluorines are good, and if you add all those electrons that you just put down, that's a total of 18. So you have 2 more electrons to put down, and if you notice, nitrogen does not have a complete octet, it only has 6. So you need to put those 2 valence electrons on nitrogen. If you count all of those electrons up, you'll see that you've accounted for 26 valence electrons. A good way to check is ask yourself, how many valence electrons does fluorine have? We said that it has 7, and if you notice, fluorine has 3 lone pairs, so that's a total of 6, plus that 1 that it's sharing with the nitrogen, that makes a 7. You can do the same thing for nitrogen. Nitrogen comes with 5 valence electrons originally, so the lone pair makes 2, but then it's sharing 1 with each of the fluorines, so that would make 1, 2, 3, and then the lone pair 4, 5. So that's a total of 5. That makes sense. You've accounted for all the valence electrons and you've completed everybody's octets, so we can move on. What if I asked you how the Lewis structure of carbon disulphide looks like? Well, you count up how many valence electrons is involved. Carbon disulphide is CS2, so carbon has 4 and sulfur has 6, but you have 2 sulfurs, so 6 times 2 is 12. 12 plus 4 is 16. We would have to decide which one goes in the center, then of course it would be carbon, and then you would put the sulfurs on either side. Next thing you would do is draw a bond between the carbon and each sulfur. That accounts for 4 electrons. You have 12 left to go. Always keep in the back of your mind how many valence electrons they originally come with. For example, sulfur has 6 that it originally comes with. Right now, it's sharing 1. So how many does it still have to have around it? Well, 5 more. So let's go ahead and put 2. And I know this is not completing the octet, but this will show you what I'm thinking about when I do these things. So again, it comes with originally with 6. Right now it's sharing 1, so you need to put 5 more around it. So 2, 4, and 5. Do the same thing for the other sulfur. It's sharing 1, so I need to put 5 more around that sulfur. Now, if you ask yourself the same thing for carbon, carbon comes originally with 4 valence electrons. Right now, it's sharing 2. So you need to put 2 more valence electrons around that carbon. Then you notice that you can pair up the lone electron of the sulfur with one of the lone electrons of the carbon, and then you have that other lone of carbon going to that other lone of sulfur. So you basically end up with something that looks like this. It's the carbon is making 2 double bonds with each sulfur. Let's count up all the electrons to make sure that everybody's octet is complete. First of all, carbon has 2, 4, 6, 8, so that's complete. Sulfur has 2, 4, 6, 8, that's complete. It's got 2 lone pairs and 2 bonding pairs, and then the other sulfur is exactly the same. So I've accounted for 2, 4, 6, 8, 10, 12, 14, 16. I've accounted for the correct number of valence electrons. Everybody's octet is complete, and in the back of your mind, ask yourself again, how many did carbon originally come with? It came with 4, and right now it's got 4. Sulfur originally came with 6. It's got 1, 2, 3, 4, and then those 2 that it's sharing with carbon, that makes a total of 6. So everybody makes sense. All right, let's do some Lewis structures of ions, anions and cations, to see how those work out. This is practice exercise 9.5. It says write the Lewis structure for the nitrite ion, which is NO2 minus. So first thing we do, we count up all the valence electrons. Nitrogen has 5, oxygen has 6, 6 times 2 is 12, 12 plus 5 is 17, but we have that 1 extra electron. It's an anion, so we have to add that to our valence electrons. So we have a total of 18 valence electrons we have to account for. Next, which one do we put in the center? It's going to be nitrogen because that's less electronegative than oxygen. So I would put a nitrogen and then 2 oxygens on either side. Next thing I do is draw a bond between each of those nitrogen and oxygen. That takes care of 4 valence electrons. I have 14 more to go. So the next thing I'm going to do is ask myself, okay, how much does oxygen originally come with? It comes with 6 valence electrons. Right now it's sharing 1, so I'm going to draw 5 more around it. 1, 2, 3, 4, 5. Next thing I'm going to do is do the same thing for nitrogen. Ask myself, how many valence electrons does nitrogen originally come with? Comes with 5. So right now it's got sharing 2, 1 with each nitrogen. So I'm going to go ahead and put 3 more, a lone pair and then 1 single electron. And then I'm going to ask myself, okay, so again, oxygen, the other oxygen comes with originally 6. So I need to put 1, 2, 3, 4, 5. But somewhere along here, I have to put an extra electron because I asked myself how many they originally came with, but remember there's that 1 more electron. So I'm just going to go ahead and put it right here in this oxygen. Now I've got to ask myself, okay, let's see where I can make bonds, because obviously the nitrogen is not complete octet and this oxygen over here is not a complete octet either. So I can go ahead and take this lone electron in the oxygen and this lone electron in the nitrogen and share a bond. So that would make it look like this. If you count up all the electrons, first of all, let's see if everybody has a complete octet this way. And you see that the left oxygen has a complete octet, 2 lone pairs, 2 bonding pairs, that makes 8. Nitrogen has 2, 4, 6, and then that lone pair, that makes 8. And then the other oxygen has 2, 4, 6, 8. That's complete octets for everybody. Let's make sure we've accounted for 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's 18 electrons. The only other thing I have to ask myself is, okay, this is NO2 minus. So there has to be a minus charge on one of these atoms. Which one is it? This is where asking yourself how many valence electrons they originally come with comes into play. Oxygen comes with 6. If you notice, the one on the left has 1, 2, 3, 4, and it's sharing 2, so that's 6. Okay, good. The nitrogen has 1, 2, and it's sharing 1, 2, and 3, so that's 5. And nitrogen comes with 5, so that's okay. What about the oxygen on the right? It's got 1, 2, 3, 4, 5, 6, and it's sharing that 1 with nitrogen. So that makes it a total of 7. So it has 1 more electron than it originally came with. So therefore, the negative charge must go on that oxygen. I hope that makes sense to you. We will do these over and over again. We'll practice these a lot, but I'm going to go ahead and start talking about formal charge. The concept of formal charge is very simple. So, for example, if I had formaldehyde, which is CH2O, and I asked you, okay, give me the Lewis structure for formaldehyde. If you were really good, you would figure out that there's 2 possible structures that completes the octet for everybody and makes sense as far as the charges and the valence electrons. These are the 2 skeletal structures of those 2 possible structures that you can have. So the question is, which one's correct? If they both satisfy all the rules, which one is correct? You can answer that by using this concept of formal charge. Formal charge is the difference between the number of valence electrons in that isolated atom, okay, so the atom by itself, and the number of electrons that are assigned to it in the structure that you have made. Basically, the rule is, and I'll show you how to do these in class, but if you end up with no formal charge, that's the best and that's the most plausible structure. Large formal charges are less plausible than smaller ones. All right, so the smaller the number of formal charge, the better. If you have the same formal charge on both different structures, then use the one that places the negative formal charge on the most electronegative atom. This sounds like a lot of stuff, but I'm telling you, once we do it in class, it's super easy and it actually helps you. I wanted to briefly go over the formaldehyde example. If you look on page 391, the example 9.7 deals with this. They draw the Lewis structure, the 2 different Lewis structures, and the one on the left has a negative charge on the carbon and a positive charge on the oxygen, which seems very odd, but it does complete all of the rules that we have to follow for doing Lewis structures. And then the one on the right also completes all the rules. So if I wanted to find the difference in formal charge, I would draw up a little table that basically shows the atoms. So I have H, C, O, and H, and then I ask myself, how many valence electrons do each of these originally come with? Well, hydrogen is 1, carbon is 4, oxygen is 6, and hydrogen is 1. How many electrons are assigned to each of these atoms in this compound that I have drawn? So the hydrogen only has 1, so that's 1. The carbon actually has 5 valence electrons around it, so that's different. And then the oxygen actually also has 5 valence electrons, and then the other hydrogen has 1. So if I take this difference, if I look at this and I subtract, 4 minus 5 is -1, 6 minus 5 is 1. Okay, let's do the other structure before we can decide which one's more plausible. So if I break it up, I'm going to do the H, and then the carbon and the oxygen. I draw up my same little table. I ask myself, okay, how many valence electrons do each of these guys originally come with? Hydrogen 1, the other hydrogen 1, carbon 4, and oxygen 6. Same thing as before. How many electrons are assigned to each of these atoms in this compound that I've made? Hydrogen 1, the other hydrogen also 1. If I count up the electrons around the carbon, you'll see that it's 1, 2, 3, 4. And then the oxygen has 2 lone pairs and 2 bonding pairs, so that's a total of 1, 2, 3, 4, 5, 6. What is the difference between these numbers? Completely 0. So this structure is more plausible because it has the lower formal charge value. That's what formal charge does. It basically tells you which structure is more plausible, and you could do this with 3, 5, 7. If you can come up with 10 different structures and they all follow the Lewis structure rules, then you can use this concept of formal charge to figure out which one is the one that you should keep. Alright, that's it for this video. See you later.